Okay, so we start first with Aditya's questions, and which could be also your question. So for today's lecture, first we will have some introductory discussions, and then we will go back to the actual content of this lecture. So I put a condition as V in is more than equal to 0, and his question is why. So let's look at this condition from perspective of CMOS technology and all CMOS circuits. And no matter what is the technology, whether it is SOI, FinFET, or planar MOSFETs. In all of them, we have one thing which is a fact, and we need to be careful about that. In these technologies, you have parasitic PN junctions. And to operate the circuits correctly, you need to make sure that these PN junctions will not really create any problem in the real operation of the circuit. So therefore, say for example, for an N-channel MOSFET, you have a P-type bulk. And for the P-channel MOSFET, you have an N-type bulk. While source and drain are different from the bulk. Therefore, you have right away two parasitic PN junction over here, for example, for NMOS, they appear that way. If you want to create an approximate lumped model, similarly for P channel, they appear the other way around. These diodes have to be reverse biased always. Now, to ensure that is happening, unless, a user or a designer has enough experience how to deal with the conditions under any value of the input signal, we create a kind of constraint and say that, see, to make sure that your devices will be always in the condition, unless on purpose you want to turn on this diode, you need to keep them reverse bias. Now, to keep them reverse bias, for each and every diode, you need to take care. This is not very easy when even you have an analog circuit with, say, 500 transistors, or you have a mixed signal circuit with, say, 100,000 transistors. So that's not practical. So therefore, what they say is that you bias the bulk as one of the conditions. You can, of course, bias it by shorting it to source or drain, but these are conditions that we have to be careful about it. So let's now consider a simple rule which will help everybody. So this simple rule says you bias. Now, this is a P-type semiconductor. Therefore, the best way is to connect you to the minimum supply which is available in the technology or in the circuit eventually. So therefore, you connect it to your minimum supply. That means here we will have VSS. Similarly, for the P-type, say you connect it to VDD. This is a generic rule. Now, if all your signals are between VSS and VDD, which is practical, again, in special cases, we design even for signals which may go beyond their supply rails. Then, these diodes are 100% guaranteed they will go in the reverse bias region. Worst case, they will be in zero bias. It is not possible for any of these four diodes with this condition and condition of the signals which are within the range of the supply, all signals. So I just write in general any kind of signal in the circuit. If I put this condition, means they can be very close to VSS, very close to VDD, but within this range. It is impossible for these diodes to turn on, right? Now, what does it imply on the signal? If the signal has different polarities, positive, negative, it can have any value. We need to work with VSS and define the VSS in a negative supply. For example, You may say that, okay, VDD is say 1 volt and VSS is minus 1 volt. You design a system with this consideration and everything is referred to minus 1 volt. So your minimum supply is not 0 anymore, it's minus 1 volt. It will work, everything is minus 1. Therefore, signal also can be negative. Another product uses supply of minus 2 volt. Now, how you can take care of these two systems when you want to integrate them or if they want to work with each other? So therefore, it's a problem of integration across all systems, all designs. So therefore, the best thing is that let's at least make a standard minimum supply, single value. Now, what would be the best single value for that minimum supply? Naturally, if it is 0, that's the best thing because it will be same as ground or reference, 0 reference that you need. So therefore, the best thing to take care of everything across all designs, all integrated circuits which are designed, is to keep the VSS a standard value of 0. Now, all systems now will be synchronized. Eventually, they will not have any problem. What is the implication? It says that you cannot apply directly negative signals to these systems unless in your design you are very careful about situations that you have. Or you can later at the boundary you have a circuit which converts eventually everything to 0 reference signal. Now, what does that mean? Means if you have a sine wave, this sine wave cannot go below 0. But you cannot distort a sine wave by just cutting half of the cycle. What we do, we add what we already know from analog circuits. We add a common mode level. By adding this common mode level, now we would be able eventually to get a standard way of using these signals and systems, right? So therefore, the main reason I said this input should be more than equal to 0 is just because to be compliant with VSS equal to 0. And this is very helpful. And that's why very well we have, even for arbitrary signal, this is not 0 anymore. This is some kind of common mode level. And the minimum value of signal with this common mode level is ensured always will be more than 0. Same goes here. Say this is the mean value. So it is ensured is more than 0. Now, no malfunctioning or error will happen in these designs by this precaution. Yes. Yes, that's also a correct point. Peak may go above VDD. So now, in principle, as far as design is concerned, we don't have any problem. We may even design circuits in which input signal can go above VDD, and they exist. However, you need to take care of one point. This gate oxide, which is between the gate and the channel, and the reverse bias junctions, have a limited breakdown voltage, and specifically this gate oxide. So if you go above VDD, you need to make sure that you are not crossing the limit on all these two terminal voltages. And usually these two are the limitation, not even junction. These are breakdown voltages. So we need to make sure that these values are less than the V breakdown, specifically with respect to the gate breakdown. This supply, which is recommended in a technology, is actually based on this constraint. For example, when you hear that 180 nanometer has a standard value of 1.8, or 130 nanometer is 1.5, or 65 is 1 volt, or even 40, 45 or 1 volt, is because of the breakdown. Of course, there are also high voltage devices in the same technology. For example, technologies which have the standard supply of 1 volt, they have also the devices which can operate at 1.5, 1.8, sometimes 3.3 standard supply values at system level. But those devices are not the core standard devices of that technology. These are devices with a higher oxide thickness, which are called thick oxide devices. Those thick oxide devices naturally don't have the, for example, ion or current drive capability of core devices, but still they are available. And in fact, you can find designs at 1.8 volt, which are in 40 nanometer, because now they use those devices. So there are in fact more than one type of transistor available. What I am right now talking about in the class for now is about core regular devices of any technology, which are bound to the supply. Now is that clear? So that was the reason I put these conditions. Okay. So Sanketan asked this question: why do we use only periodic signal for FFT? In fact, FFT and DFT are subject to this assumption. What if we have an arbitrary signal? So answer is this: we make conceptually a periodic version of that signal because we have only a limited W. We have a limited time window for the sampling. We cannot go forever. That limited time window will tell us this is the period at which we are sampling the signal, which could be more than also the duration we want, but we get more samples. As I told you, we can have extra samples. But at the end of the day, ideally, let's say W. If I look at the signal only within a W time frame, I can consider conceptually it is periodic with the period of W, let's say. Or it is a periodic with a period less than W, if it is a sine wave and my window is more than the period of the signal, or it's any arbitrary periodic waveform with a period of the signal less than W, so I can consider their periodic is still within window of two next W and next W and next W, which are not there, but I will make a signal like that. And that's why we are in the notion of periodic signal. So nothing will change practically, because our window of the existence of the signal, like existence of the signal is limited to W only. So therefore, we can always imagine that, okay, it will continue and will repeat itself. Then concepts will work. That's the reason we are able to do that. So we can quickly cover the, currently we have not talked about anything about the parasitic capacitances of the device. We want to start that. But before starting that, I cover a few points, which is continuation of the last lecture. So just to give a quick recap. So we discussed about NMOS switch as a track and hold switch, along with a hold capacitor CH. And I gave you two examples. If you have noticed in the previous notes, I have added example 3. I have written a little around expanded version of example 3 in this. So here, eventually in the example 3, which is a kind of based on the previous examples, here, as I told you, we can also define the final value of the error, which is difference between the input and output when switch turns off or switch is open, as an absolute value. For example, here I have given the 3 millivolt as the margin for the error. It should not be more than 3 millivolt, and that defines the settling time. So therefore, by having that, we will continue the same solution. Already we have this expression from last example. So you calculate the track time, okay? And then assumption is same as before. We assume that input is not changing significantly, or eventually, other way around, let's say, it's better to say signal is not changing. The change in the signal is negligible within this track time. So therefore, we have effectively at the beginning, difference of the previous sample on the CH and the current input. And we want to reduce the absolute value of this difference to 3 millivolt. While we are also saying that the maximum difference at the beginning could be 100 millivolt. So we need to have these ideas about the signal so that we would be able, and the error, permitted error, settling time error, and therefore you can calculate the track time. Okay. So this is the third example that you calculate. Okay. So this is what we had before, track and hold using NMOS. So here I'm showing PMOS, just because we need both of them in some cases. Therefore, it's good for you to have an idea exactly how to look at both of them. So they are dual of each other, these circuits. Therefore, you will have either delta V, again positive or negative, that is same for both. But what will define the source now will be the opposite polarity compared to NMOS. So I think overall everything will be straightforward for you. The difference also is that if for a PMOS you are using an input like a clock, this clock, when this clock is VDD, the switch is off. When clock is 0, switch is on. So keep in mind there is this difference as well. Okay, therefore the equivalent circuit will be like when clock is 0, actually we have R on. When clock is VDD, we have the almost like an open circuit. Or at least we say again, transistor current is negligible. Okay, so and the same, rest of it will be same. Now approximate expression for the R on, if you go with the long channel approximation. So still will be similar, but here now instead of VDD, we don't have any VDD here. When switch is on, input is 0, gate input. So therefore, in the expression, you don't see any VDD, it's directly VD only, because gate voltage is 0. Therefore, source voltage is same as the source gate voltage. Okay? Fine? Fine. So now we have some idea about NMOS, PMOS, and then as of now, parasitic capacitors are ignored. Okay? So we also had a discussion about NMOS and PMOS. So because now we know exactly what would be the situation of the gate. So therefore, I'm showing when transistor is on. For NMOS, gate should be VDD. For PMOS transistor, if they are exactly at the same location like the way is shown over here, so one should have clock and one should have clock bar. So therefore, this clock bar to allow the PMOS transistor to turn on at the same time NMOS turns on, therefore they should be invert of each other. So VDD 0. So what is the range for the source voltage, which eventually is the output or input, doesn't matter. So it's eventually for NMOS, we have to be 1 VT below VDD at least. Therefore, it can start and reach to VDD minus VT. And that is the way R on increases. So the worst case condition of R on will be when inputs are at the highest possible level. Of course, highest possible level will not be VDD minus VTH. It is even below that when you design, because it's not practical. Similarly, for PMOS, the range should be in such a way that source minus gate will be above VT, absolute value of VTP. VTP itself is negative. So that's why I write absolute value. Because gate is grounded, directly it becomes source, which is signal or output, same. So that covers any value which is above absolute value of VTP. So as you can see, we have two range of values, VDD minus VTHN and VTHP till VDD. Sorry, 0 to VDD minus VTHN and VTH absolute value of VTHP to VDD. We have to make sure these two have overlap. In fact, that was also one of the questions last week. I think you asked as well. So yes, and that's why at that time I told you should be VDD should be more than summation of the absolute value of the two VTH, and that's the reason, because we want the VDD minus VTHN to be definitely more than absolute value of VTHP, so that there is an overlapping of the two conductive region of the two switches. And that's why we have the condition of VDD more than absolute value of VTHN plus absolute value of VTHP. VTHN, of course, is positive. So this is the condition. Based on this condition, if I put two switches in parallel, not exactly parallel, their gates are inverted, but their input and output are same. So I will get some kind of equivalent parallel R-on resistance this way. Like at the low values of V in, NMOS is dominant and determines R-on of the switch, and this is called complementary switch, similar to the complementary transmission gate that you have in digital. But here we are using it as an analog switch. Therefore, we are operating over the entire range, not only logic low, logic high. So it's the entire range analog, and there are many values in between. Okay, but one thing always comes, see, it's very interesting. Any solution has its own consequences, its own side effects. So what is the side effect of this technique is we need to make sure clock and clock bar are well synchronized. If they are not, one of the switches will turn off while the other one still is not turned on. And therefore, you will have, again, distortion. There will be a kind of dead zone. When switch turns off, eventually effective or on goes up and again goes back as a function of time. So these are the practical issues that you need to consider. In Razavi's book, in the same section that I have given as reference for you, he has given some approximate analog equivalent of the solution, but there are other solutions as well. So you may ask why clock and clock bar synchronization is so difficult. It is indeed. It's not difficult, but it's not straightforward. It's not like that you say that, okay, I generate clock bar and it becomes just same as the invert of clock. Suppose you have clock on the left side and you generate clock ball on the right side. What is the problem with this circuit? Exactly. So this is a textbook circuit. It doesn't work in practice. In fact, you can't find this case unless if you are okay with the phase difference between. So in where you want clock and clock bar to be synchronized, simple inversion will not work. Even if you make it a buffer, will not work. So you may say that's okay, so we will do this. So this is a centralized clock, and then we pass it, through a smaller inverter. On purpose, I show it smaller so that it creates more delay. So this is actual clock. This is, say, master clock. And this is clock bar. Now, what is problem with this circuit? On purpose, we use a weaker inverter and two stronger inverters, so that the delay of two stronger inverter will be same as the delay of one weak inverter. Why this is not working in analog? Which may work in digital, even in digital doesn't work. Any guess what can happen? Eventually, many textbook circuits won't work in practice. They teach you concepts very well. That's why we need to start from those practical circuits in textbooks, which still try to solve practical problems, but still are not enough practical to become actually a quite live circuit on the chip, physical circuit. See, one of the problems in all technologies, no matter what it is and any domain, is that you cannot just make two things which are exactly the same, right? Therefore, if there is a wafer of this integrated circuits, every die on the silicon wafer, these dies are not exactly same. Transistors on these dies are not same. So when oxide, for example, silicon oxide is grown or formed in any manner, so how you can ensure that the devices on left side of the wafer and right side of the wafer exactly will have same thickness? So therefore, if for one side of the wafer you make this solution, for the other side of the wafer, actually exactly these two don't match. Again, you will end up a difference between the delay of the two parts. So this is called process variations, and process variation is a fact and source of many innovations. In fact, I have not come across any analog design or even mixed signal design where process variation has not been a bottleneck or a problem. Otherwise, designs become relatively straightforward. And therefore, that's the source of innovation. So this also doesn't work. So there are other techniques which can be, for example, what Razavi says that, okay, let's put, instead of this, say, for example, path, so let's put 2 inverters and then say have complementary switches and then put an inverter and then still try to make them matched. See, exactly same transmission gate. Eventually it's a transmission gate, but in analog we have, that is like a switch, analog switch, but they are always on. Like this is grounded, this is VDD, and then he says, but this also doesn't work. Though it is written in the textbook, but it may work. Actually, it depends how much variation exists. How fast is the clock frequency? There are many factors as well. You may be able to still avoid, for example, your resolution of the track and hold circuit may not be very, very kind of fine. So I gave you example of 3 millivolt in the example 3. So you may have, say, 20 millivolt. You may have 50 millivolt. If that's so relaxed, actually this may not be a problem. Therefore, it all depends on how much precision you want from your system or your circuit when you design. So there are techniques, of course, which are used, for example, in SERDES systems, serializer, deserializers, which are used for clock recovery, which have clock recovery, clock extraction. And they deal with extremely high frequency clocks. But I want you to have really, if you are interested, just explore. In fact, you can simulate. For example, suppose you have this. And one of them is actually a buffer only, because one is clock, one is clock. So what you are doing is that you're loading each inverter or buffer. All these inverters are like buffers. At the end of the day, you want to drive clock gate of all switches, therefore you need buffers. So you load each one of them with the other one. You cannot directly short them, so you invert them and short them. So these techniques are used in SERDES systems, which are dealing with gigabit per second operation. And they continue even with the chain to make better and better, so multiple stages. But this is for your information only, because in this course, we are not really looking at clock generation and clock recovery techniques. That's again a separate topic. But just for your information, yes. This one. See, this is a switch which is always closed, but it has its own delay, because we know that there is a time constant associated with that. There is a parasitic cap at the input of inverter. So therefore, it's like you have a track and hold which is always on, of course, here. So it's like an RC circuit. So you put an RC circuit, but R is made by transistors. So you are trying to make the delay of this path, because this has 2 NMOS, 2 PMOS. This has 4 NMOS, 4 PMOS. So, and it's likely to compensate. You can adjust values. The delay of this path to be exactly delay of this path.
It's still going to be subject to process variation.
It is still subject to process variations, yes. But why, for example, Razavi says that this could be one of the solutions? The reason is because you don't have 3 inverters here. If you have 3 inverters, you will end up in the same problem of 1 inverter difference between the 2 paths. And again, the mismatch due to that extra inverter. It says that, okay, we don't put inverter, we put a switch which is always on. See, the problem with the switch which is always on and still is subject to the variation is that, though here you have tried to compensate one of the inverters with that switch, but this is always a resistor. inverter actually operates as an amplifier in some range, but with high gain. That's why you are not matching them properly. So that's why this also will have the similar problem. But here, eventually what you are doing is that you say if one of them is strong and one of them is weak, anyway they are coupled to each other. So therefore, always one of them doesn't allow the other one to move. They have to move together. See, they have to work together. Otherwise, this node and this node will be stuck at VDD upon 2. The only condition this can work where everything is analog and fixed is VDD upon 2 everywhere. But because here you are driving, so therefore you have logic levels here. So it doesn't stay at VDD upon 2. But then there is a delay. So therefore it is not allowing. So eventually it's like that. Suppose this wants to change, right? But this buffer, suppose this changes faster. This comes forward to change this node. But this is already, and it's faster. This has not changed. Therefore, this output of this vertical inverter, input and output are supposed to be same for a short time, and they will not be. It's like this inverter 2 is fighting with the variation at this node because it already taking input from the slower inverter or slower buffer, or this could be 2 inverters. So therefore, because of this continuous fighting, you are coupling them to each other. So therefore, the fastest element needs to wait for the weakest element. So eventually, they will reach to the kind of synchronized speed. So, but as a disclaimer, we have not used this technique on the chip. So we have actually used the similar techniques on the chip, and it has worked. But I don't know about really 2-digit number in gigabit per second, because we have not gone beyond 12.5 Gbps, and that also we have used a well-synthesized clock bar controlled by an instrument. So that's why we didn't get into the clock generation. Okay, so this just as a disclaimer, I have not tried this technique, but these are published research papers and fabricated measures. So they are there already. Okay, so now here actually the next part, we want to start with the parasitic capacitors, because till now seems everything is fine. All we need to design is a 2 parameters we have to design: aspect ratio of the transistors for PMOS and NMOS, if we want to use both of them. If the input voltage range is limited, we can use one of them. And it would be better, because then we don't have the problem of clock bar. But and value of CH. But we ignore the effect of parasitic capacitors, and that's why now we need to enter into parasitic capacitors effect. But one thing before that, which is related to your first tutorial. So now you got the account, and also you have the first tutorial, first part. See, second part is PSS analysis, that will come later. First part, which is FFT, you have received also the example, but you need to run it as a practical assignment. So we will have the first assignment, which is a practical. It will not be counted as a part of 2 assignments I told you we have for the class before mid-sem exam. This will be a practical assignment. So there will be a practical assignment. I will post on Moodle during weekend. You only run the same example and reproduce the results, and then submit your report. And in this course, all the time, for every assignment, project, anything, of course, we have one project only. So you definitely write and show what a snapshot of the accuracy options and the parameters you have for transient option, or PSS analysis setting. You take a snapshot and show it because it shows at what conditions you have simulated. FFT is extremely sensitive, and all these mixed signal circuits are extremely sensitive in the way that you set the options. Okay, then we start with the effect of, and these are transistor capacitances. Effect of MOSFET capacitance. Actually, I mean, at the end of the day, let me put transistor because it's not limited to MOSFET. Transistor. So what are these capacitance effects which are happening in transistor? So they are happening at different parts. But if to show you in a kind of equivalent lumped model, which is an approximate model, you can consider we have this kind of capacitors. One is a capacitor between gate and source. One is between gate and drain. One is between gate and bulk. So since it is too small to show that way, so I will show it this way. External, and this is the channel of transistor. So I connect them this way. If I want to show the bulk, you have also parasitic capacitances between bulk. And this bulk is connected to some bias. Here, for example, minimum supply, which is 0. So therefore, because this is 0, therefore effectively these parasitic capacitances can be shown as a capacitance between source and ground and drain and ground. So this makes it easier. So this is CGS overlap. This is CGD overlap. O stands for overlap. This capacitor is C gate channel in general. If channel doesn't exist, so transistor is off, so it is gate to bulk. And these are junction capacitors, which are well known. So we go with this simplified model, which is good enough for investigations and design. So the capacitors which are at the source and drain, but between source and drain and ground, can be clubbed with a hold capacitor as well as the output resistance of the source. Therefore, really we are not worried about them. So inside we don't need to show them. Therefore, what I will do for simplicity, I will remove these capacitors because they can be clubbed. So we will effectively end up with 3 capacitors. Now we have 3 capacitors. Which one is more important? Actually, honestly, all are important, but we need to see how they are operating within the way that we are operating the switch, analog switch. Now let's look at the approximate model that we had. So approximate model was something like a voltage control resistor. So now there is a parasitic capacitor here, and here, and here between the, so if I take it, I make this as say 2 resistors, I can say, for example, approximately show it this way. So effectively now we have this model of our switch, approximate model. This resistor actually is the channel of transistor. representing the channel of on transistor, because this is when switch is on and it is in ohmic region. As we discussed, if the difference between two consecutive samples is not very high, say 100 millivolt, 200 millivolt, it's a good assumption to consider transistor which is operating as switch is always in the ohmic region. So we'll see that what are the one by one problems. So now what I will do is I will also remove this switch. I will replace with now track and hold circuit. And then see that as a designer, what we need to consider to design the switch. Okay. So this is clock. For now, I write V out of T because now we have capacitors. And to see the effect of those capacitors, I can limit it to one single instant at the end. So we want to see that what happens when switch turns on. When it is off, really doesn't matter what is happening because at the end of the day, this switch is off. Though still we have coupling, but this clock is silent. The problem starts when this clock has a transition. At that time, which is the start time for this discussion, we will have the problem. So therefore, let's say the first problem. Let's say we have almost like an ideal clock with sharp edges. So let's look at this circuit again. So no, let me look at it here itself. So we just draw the capacitors. First, I show these two overlap capacitors. So what can happen in this circuit, which have two capacitors from clock terminal to the input and to the capacitor CH? Let's assume this edge is very sharp at the beginning. So what kind of effect could happen here? You have a circuit like that. So what kind of effect can happen just at the during transition? Yes? Vout will experience this transition. Very good. And you know what is exactly that effect? It's because, yes, you say. Clock fit through, very good. So you see this parasitic path. So therefore, if there is a transition here, when there was no capacitor here, there was no coupling. Now the clock node and output node are coupled through a capacitor. So therefore, right at that instant, if the say clock is very sharp and quick, so you have a condition like this. This is the edge, and specifically I showed the edge because this is not true for all instances because we have a capacitor on the transistor on the left. We cannot ignore it. I'm just talking about that a particular edge. For the case, clock edge is very sharp. Now you see there's a capacitive division. So therefore, you will experience the first delta V out. Delta V out 1. Or delta 1 V out. Let's say delta V out 1. The first effect. It's a capacitive division. How much is this delta V? So it is VDD, right? So this delta V, which is VDD, will get divided. So therefore, the value will be capacitive division. So this is the first thing that now we have. So the output will experience a positive transition. It's positive because delta V clock is positive when transistor goes from on to on, off to on mode. If CH is high enough as compared to CGDO, in such a way that the whole this delta V out is quite low, this effect is negligible but not necessary. So therefore, this is the first thing. Therefore, what will happen is you may see whatever is the steady state value, so you have a transition. Even if the new value of the input is less than the previous output, so you have a positive transition and then it will start going back to the new value. So this effect we didn't have. So our initial condition was different. We were starting from the previous value to calculate a decay again going back to the next value. So now there is a transition. This is the first effect. Now the second effect. This was when transistor goes from on to off, off to on. We have also one thing which is off to on to off. So therefore, now when transistor actually wants to transition from on to off, there are two things here. One is the clock, and one is this capacitor, which was between gate and channel, effectively. What is stored in the channel? Charge, right? It's a capacitor. When a transistor goes from on to off, the channel will become free of charge, right? Because those electrons which inverted the channel to n-type, now they have to go back through source and drain terminal back to the ground. We ignored this effect when we were analyzing the switch without capacitors, but now we have to consider that. It's a capacitor between the gate and channel. So what will happen for that charge? For example, just to show the conceptual diagram or kind of circuit. So these electrons are here. When clock goes low, so still we have that clock withdrew effect. Now one more effect also will come. So therefore, here not only we have clock withdrew, but we have one more effect. This charge eventually will be depleted through source and drain terminals. So where does it go? If it comes towards the V-in, so it will flow to whatever circuit generates V-in. Therefore, it has to have that provision not to change V-in. But let's assume for now, we are not talking about the circuit which produces V-in or the sensor from where V-in is coming. We are talking about this side, which is under our control. We assume everything is fine over there. So here they will come over CH, and they will come over also this capacitor. But CH usually is a large capacitor, so therefore it's like a low impedance path. So it will draw the charge. So therefore you have some delta V out, which is related to the fraction of charge, which is coming on CH. How much is this delta Q? Answer is we don't know. It could be very low, but what is the delta Q max? Absolute value. Anybody can tell? What would be the worst case charge which can actually come from channel on the CH? Worst case value of charge, amount of charge. CHVDD. Why CHVDD? See, this is coming from channel. Therefore, we need to see how much, sorry, who talked? See, we need to see how much charge was stored. Because this charge is getting discharged on the capacitor. So how much charge was stored here? That's the answer, right? Total charge. That's the worst case. Means that worst case, see, analog mixed signal designers design for worst case. In fact, all engineers who are designing a good thing, if you want to design for a earthquake resistant foundation, you consider 8 eventually degree, which is not practical, right? Hardly happens. It's always 7 point something at worst. So therefore, that's the same. Let's assume no charge goes on the left. Everything comes on the right. How much is the value of this charge? See, we already had this discussion when we were talking about Aron. How much charge is accumulated in the channel of transistor? Yes, the overdrive, gate overdrive, right? Gate overdrive multiplied by the capacitance, the whole capacitance, assuming because it's ohmic region. It is actually the capacitor between gate and channel we are talking about. It's a gate capacitance. So therefore, the worst case value, let me show it as a bullet item, so otherwise it will be look like a minus sign. So this delta Q max absolute value, because here is electrons, that's why I talk about absolute values. So fine, so therefore this will be W multiplied by L C ox. So here we are talking about NMOS, VGS of transistor, which was say VDD minus say whatever was stored at that time, right? So we call it say Vin of N minus VTHN, right? Q equal to CV. This is the worst case charge. And as you can see, it's a function of Vin. Therefore, the charge which actually goes on CH itself is a function of Vin. Also, the initial voltage, the actual voltage expected on CH itself also is a function of Vin. Therefore, how much is the already Q and CH? Because this is end of track time. Now we are moving to the whole time. This was CH multiplied by voltage across that, which is Vin. Right? This is the real charge, desirable charge, which is stored. I assume that the output almost reaches to Vin at the end of tracking, that a few millivolt we are not considering here. But now we have a change in delta Q, and worst case is this. Therefore, this value now will change and becomes a, say, Q2CH. And this value is same as what was given during tracking at the end of track cycle minus, because these are electrons, WL Cox VDD minus Vin minus VTH. So this is eventually showing the change in the charge. This is error, because when it comes to the capacitor, there is no way to discriminate it from the original charge. When you have the clock fit through and you have a sharp rise, still it will continue to decay and the effect will go away. But this channel charge, which comes on the CH, is actually a problem. So one has to be aware of that and design in such a way that this will not create error, which will degrade the resolution of the track and hold circuit. So this is eventually effect which is called charge injection. So let me remove this clock fit through so it's not mixed with the clock fit through. So this is charge injection. What does that mean? Charge is injected from channel to CH. So we need to be concerned about, and this is the worst case, therefore this is eventually delta Q max, so this is worst case. Worst case in the sense that when the maximum charge is given. Now actually if you look, if we organize this, eventually means that the effective value of CH now will be CH minus WLC ox multiplied by VE. And the rest is a constant value. So therefore, if I want to write it, I can write it here this way, equal to CH minus WLC ox multiplied by VE plus some offset voltage. Offset voltage is less or more a function of technology parameters and size of the switch, like and supply, say VDD, VTHN, WLC ox. And the part which is related to VE will appear in the coefficient of VE. This is the first level approximation. Okay. So I think everything is correct. Dimensions also match. The first thing in debugging always is to check if dimensions match. So this is that offset voltage. Offset voltage is not a problem if it is fixed, because it is equivalent by saying your final output is shifted by some delta V. Still, you are not losing information. But the point is that we don't know how much charge will come. We assume the worst case. This charge actually could change from 0% to 100% of the channel charge. So therefore, that's why it will bring some kind of distortion. If it was still fixed and say max value, still we have some idea. The whole effect is the effective CH is reducing. But the point is that it is not fixed, and that's why it will bring distortion. Fine. So therefore, this is now we have charge injection and we have the clock withdrawal. Coefficient of V in. CH
plus W.
Oh yeah, sure. Yes, sorry. CH will be more than, but yes, correct. Eventually means that if you want to really show it the way you had, see, you were supposed to have CH into VE, right? To be precise, V in N. So now you have one extra term, which is WLC ox upon CH plus offset voltage. So therefore, while clock fit through is not the first concern, at least as we see, charge injection is a concern. Same goes for p-channel transistor. Problem is same, only polarity will change. Polarity of charge will change. Polarity of signal will not change. All are positive. But polarity of the charge will change. But it's the same. Effectively, you will get a gain. It's like you have a gain now. I mean, it's more than one. Your track and hole is giving a slight gain. But the problem is this gain is not fixed. How to solve the problem? We need to make sure that at least most of this charge will go somewhere else, right? So one of the very common techniques, which sometimes works, sometimes doesn't work in practice, is that you have this switch. And we know that the problem is the channel charge. When a transistor turns off, this charge goes away. When it turns on, it brings the charge to the channel from same terminals, specifically source terminal. Why not to add a transistor which will turn on when this transistor turns off? And that transistor, we don't want to do anything. We just add it's called dummy transistor, to just create a path for the charge. That's it, no other effect. And this is simply, whenever you want to create a dummy transistor, it's enough to short source and drain. Indeed, it becomes like a dummy. It can't do anything. It's a two-terminal device for you. Bulk is connected to ground. So it's not counted here. So it's a two-terminal device. Now suppose I have this, and all these nodes are same. So therefore here you have a still CH. All we want to do is that when main transistor turns off, this transistor to turn on. And this transistor only channel will form. Nothing else will happen because we have shorted already nodes. So therefore, what will happen? The channel charge which was here, say if we are giving clock here, we will give clock bar here. Again, here also we have the same thing. We have to make sure that these two are synchronized. So this needs charge. So charge actually will go to the channel of this transistor. Oh, no, I should not show it there. Here. Right? So therefore, it's like you from one bucket, it goes to another bucket. These two transistors have to be exactly same. So that the same amount of charge which goes here, comes out here can go here because they are exactly experiencing similar condition. And to make their dimension to be exactly same, if this is say W upon L, this will be because you are shorting, so you have eventually two terminals equivalently. So therefore, the best way it works if the size of transistor is half of W upon L. Because it's connected only to the drain or source, either of this one of these terminals. This is usually working well if you make it half. But this is not also an exact number. So you can actually see that what would be the best way. But there is also a very interesting aspect over here. You know, this CH anyway is here as well. In fact, if you want to show this circuit properly, it's better to show this dummy transistor vertical rather than horizontal. It will give you a better perspective. I draw it here. You see how it changes the perception of the circuit. See, if suppose entire charge comes, actually you may need to make larger W by L for the dummy transistor. We don't know how much, that's why they get it half. Actually, you can draw this circuit this way, which is better. Say I connect both sources here, say. Doesn't matter, actually depends on what terminal will be source. Okay, it's very crowded. I put source other side. So it's actually this way. This is better, right? This schematic better shows the concept. At the end, it's like you are putting a dummy capacitor that also needs charge, right? So therefore, it will draw the charge from this channel, and less, we can't say 100%, but less charge actually will come over CH. Okay, and this is at the falling edge of the clock, which will be here, rising edge. So this is helpful because we have to avoid this V-independent charge injection, because as I said, that worst case I consider is only one case which may happen, may not happen, because always some charge also goes into V-in. In fact, what fraction comes also depends how fast clock changes. So there are so many factors affecting the percentage of charge exchange between the two sides. So some charge goes from V-in, some goes to V-in, some goes to CH. Okay, see, dummy eventually switch is a very common technique. However, you need to make, let me write also dummy switch. However, with proper, and now you can understand how proper simulation matters. Because sometimes you may not see clock fit true still is fine, but you may not see proper charge injection, and just because your simulations are not right. Or sometimes you see the problem is not solved because your simulations are not right. Sometimes you see that it works very well, again, because, so it's very important to at least be consistent across all simulations and have enough precise simulations. First order simulations can be always in liberal mode of a spectre, making it fast just to get some idea. But when you want to actually see the effects, you need to do a very precise simulation. But because it's very time consuming and also creates a lot of data, transient files or PSS files become large. So it's better always to have precise simulations only with a limited number. This is also a skill, how to simulate the circuits and then how to really get the right thing. In fact, one of the references in your tutorial 1 is all about how to simulate the circuits, specifically in transient conditions. Okay, so we did this as well. Now the question here is, what do you think will happen for the clock fit true in this circuit? So therefore, what I'm adding, so therefore we didn't talk about clock fit true when we were talking about this technique. But let's say we have now this parasitic capacitor as well. So now what do you think will happen for the clock fit true? Here also we have parasitic. And in fact, these two nodes are shorted. Be careful, the two transistors are, so this CGSO plus CGDO of dummy are here. So what do you think now will happen for the clock fit true in these conditions? Because we didn't have that dummy transistor when we discussed. To simplify the circuit will be something like that. If you go with the same sharp edge, and we were worried about the case, sorry, the clock. Actually, both of them. Let's just consider both. Right now, for example, falling edge. In fact, clock fit true, when we look, we should look at both of them and see which one really, and what is the effect of each one of them on the circuit. Because when the transistor turns on, clock fit true still will go away, as I showed you, and it will settle. When transistor turns off, so this clock fit true needs to be taken care. So I'm just drawing the equivalent circuit. So it can be summarized something like that. Sorry, not here, it's not. It is clock bar. In fact, I can remove this transistor as well and just show clock. So this is CGDO, CH, and then here I have CGSO plus CGDO dummy. Clock bar. And in fact, if the transistors are sized that way, summation of these two will be equal to CGDO of the switch, if we go with half size. Okay, now you can say what will happen if the clock goes from high to low. Okay, now let's understand what we need to do to nullify the effect of the stored charge in the channel. May not be completely, but at least partially. So at the time exactly when the clock goes low, so this is for n-channel switch. So in this transistor M, say, so we know that the charge which is stored in the channel is Cox WL VGS, which is eventually VDD minus V out N minus threshold voltage of n-channel transistor. So it's not very well determined what fraction of the charge will actually go into the capacitor CH. It could be the entire charge, which is shown over here. CV is the charge, or a fraction of that. For example, if you have a complete symmetric transfer of charge, half of the charge. So therefore, what we need to do is that to see whether we can find a way that this stored channel in the channel that I conceptually show this way, and here are electrons, to move to a different direction. And for that, one of the common ways is to imagine if you have a dummy switch. This dummy switch effectively is a capacitor, which only we keep that capacitor, but we want to make it exactly same as switch. Therefore, we don't use a capacitor, we actually use a transistor exactly of the same type of the switch to divert the charge towards that transistor. So imagine that we have transistor, say M1 as a main switch and transistor M2 as a dummy switch. So that means that if we have this dummy switch, which is only as a capacitor, therefore we connect the drain and source terminals together, bulk could be still connected to the ground. And as we have considered before, for now we ignore effect of body effect on the variation of threshold voltage. Now, if we consider the case when transistor M1 turns off, at the same time we turn on transistor M2, so transistor M2 needs to receive the charge, and therefore there is a path for the charge to go to the different path rather than CH. So we can show the diagram this way, or we can turn M2 and make it a parallel element, because the drain and source of M2 anyway are shorted, as it is clear in this diagram. So therefore, to turn on the transistor M2, we need to give the clock bar to the switch. Now imagine the charge which is stored in the transistor M1 is entirely transferred to transistor M2, then we need to make M1 and M2 of the same size. If half of the charge is going from source of M1 in this diagram towards CH, so we will make M2 exactly of the same size, half of the size of M1, so that we would be able to make sure that the charge which is stored on M1 will be the same charge which is required by M2, so that the net charge which arrives at capacitor CH will be 0. So this is one of the common practices. However, it doesn't mean that the net charge always will be 0, because we don't know what fraction of charge will go towards CH. More often, if the clock edges are very sharp, not necessarily the entire charge goes to the capacitor CH. That's why the practice of considering half of the charge goes, because transistor M1 is in ohmic region. Most of the time, half of the charge will go to the CH is a common practice, and therefore size of M2 is considered to be half of the size of M1, which means same length and half of W. Now, if we look at this way, which is very straightforward, considering partial at least compensation of the or nullification of the charge injection, we want to see now what will happen for the clock feed-through. So therefore, we draw the equivalent circuit for the sharp edges to get a better idea about clock feed-through. So this is clock, which is going from high to low, and clock feed-through is extremely important when switch turns off, because when switch is on, even when it turns on, we have the clock feed-through, but the effect will get compensated, only it may add to the delay. However, if when switch turns off, then we don't have access to input, and therefore the offset generated by the clock feed-through and charge injection will stay on the CH, and it results in the error on the value which is sampled on the CH after clock and held on CH after clock goes low. So now what are the capacitors we see here? So we have the, say, gate source overlap over here, and then say gate drain overlap of M2 over here. So two types of capacitors, but both are overlap capacitors, and per unit W they are equal. So I call CGSO1 and CGDO2. So similarly, we have CGSO2, which is parallel now with CGDO2, because they are exactly having same terminals. So drain and source are shorted and gate is common terminal. So effectively, if I want to write the value of capacitors that we see in this figure, so with respect to clock connected to CH, the bottom capacitor is CH, we have CGSO1. And connected to same top plate of CH, we have 2 times of CGSO2. Which is connected to clock bar, and therefore we will have the rising edge of clock bar. And this is 2 times of CGSO2. It will be equal to CGSO1 if we consider we have designed for the case half of the charge is arrived on CH due to charge injection, which is the case shown in this figure. Fine. So now it's a very interesting observation here. What happens for the clock feed-through effect? So as you can notice that capacitors on the top are equal now. And amount of drop in the clock, for example in this case, is VDD to 0. Amount of increase or level change in the clock also is clock bar is 0 to VDD. So that means delta V is same for the clock and clock bar, only with opposite sign. And the capacitors are equal. Therefore, if we consider V out N, how much would be the variation in V out N due to clock feed-through? So therefore, this is due to clock feed-through. So we have the capacitive division two capacitive divisions and we use superposition principle. So therefore, if we make clock bar 0 and then we have the delta V of minus VDD, so therefore this change will be minus VDD multiplied by capacitive division, which will be CGSO 1 upon CH plus same CGSO 1. And if we go with the second part of superposition expression, for the case clock is 0 and clock bar is affecting. So the transition here is from 0 to VDD, so delta V will be positive and the amount will be plus VDD. Amount of the change in the voltage will not be different as far as fraction is concerned. Only polarity is different. So therefore, net change will be 0. That means that if we assume the half of the charge will be transferred during the charge injection due to the turning off the channel, similar effect or positive effect, eventually it's helping to reduce the effect of clock feed through. Ideally, there will be no effect of clock feed through. Practically, charge injection may not be exactly compensated because if you don't have 50% of the charge transfer to CH, but if we keep the sizes the way it is shown here, we would be able effectively to reduce effect of clock feed through. This is specifically for sharp edges. If the edges of the clock are not very sharp, so distribution of charge across the two sides more often follows very nicely the effect of impedance. But more observation and exact amount can be obtained by precise, accurate simulations. As I told you, simulations are very important. However, to be able to do the initial design, we need to have abstract models which are not far away from reality, but can give us the expressions which provide some insights into how to size switch and transistors which are used as dummy switch. So this technique is called dummy switch, and the effect on both sources of inaccuracy. There are other sources of inaccuracy. For now, we are looking at the charge injection and clock feed through. Okay.